This is a video for CSE 548 where I'll be demonstrating the remote DNS cache poisoning attack. In this attack, we will be attacking a victim DNS server running on a network remotely by injecting a spoofed name server, authority name server that would resolve hosts such as www.example.com. In the attack, any victim in the network that relies on the DNS server to resolve names will resolve any host name of example.com to our malicious actor's IP address 192.168.1.1. In order to actually attack the DNS server, we utilize a method called the Kaminsky attack. In the Kaminsky attack, multiple host names that most likely do not exist are used to force the DNS server to recursively query higher authority name servers to resolve those addresses. In the case of www.example.com, we may send out multiple queries such as xyz.example.com, yyy.example.com, and so on. When the DNS server queries for these names, we flood the network. We flood the DNS server with spoofed responses from what it would think is the authority name server of example.com. If we are able to create a good response, the server would accept it and then keep it in its cache for however long the TTL we specify it to be. And for as long as the entry is in the cache, any queries for that within that domain will lead to our malicious actor. So there are four conditions that we must fulfill in order to successfully perform this attack. The first is the response needs to arrive at the same UDP port as the source. In this case, we made the attack a little bit easier on ourselves by configuring the DNS server to only send out queries on port 33,333. The second condition that we must fulfill is that the question section in the reply must match the question in pending query. So if the query is who is xyz.example.com, the response must have this original question in the question section as well. The third condition is the query ID matches the pending query, and this is perhaps the hardest part in our scenario, where the query ID is a 16-bit field that is used to match the responses to the queries. While 16 bits is not a big number, we can something that can be easily brute forced. We must be able to send as many packets as we can, guessing this query ID in hope that it is the correct ID. This is where querying multiple different URLs comes in handy. Finally, the fourth condition is that the authority and additional sections represent the names that are within the same domain as the question, and we'll see what this condition actually is composed of when we look into the packets in a successful attack. So we will begin the attack by going into the attacker machine, where I have a Python script that generates about 10,000 URLs, all coming from one of the authority name servers of example.com. So we're spoofing this particular name server. And then our victim is the DNS server on 192.168.1.3. And of course the port that we want to send it back to is 33,333. We generate 10,000 dummy URLs in the example.com domain, from then which we try to guess the transaction ID and send out about 100 packets per URL. On the DNS server side, we will flush the cache and then start Wireshark for debugging. Let's use the DNS as a filter name, and then we will begin the attack. This may take a while, so we will come back once we find a successful attack. So I'll begin the attack now. And you can see we are beginning multiple DNS queries, and hopefully we get an attack soon. So we've let the code run overnight, and it seems like we ended up performing a successful attack. Going back into the DNS machine and looking at the Wireshark logs, you can see we've captured about 11,000 packets, so we sent out quite a lot of DNS packets. You can see the success happens over here when the line 2961 on packet 2961, the DNS server queries to the authority name server, example.com's authority name server for om7bq.example.com with the transaction ID of 8D27. And then eventually somewhere along the line our program was able to guess that response, luckily. That's why it takes a while, but once you see we get that response here on line 2972, transaction ID matches, and if we actually look into the packet, we see that the flags indicate that this message is a response. The query om7bq example.com matches the original question right here, and the answers match the original question as well. And of course we add on our name server ns.cse548.net as the authority for example.com. And then you can see here right after this successful response that the authority name server, the DNS server 192.168.1.3 will respond to the attacker, and this will be cached. And in fact, this is what we see here. If we rmdc db cache, and then let's take a look at this. If we look up 548, we'll see right here that this is registered as the authority for example.com. And furthermore, we can actually go back to our attacker machine, launch Firefox up, www.example.com, and we can see that this attack worked. We can see that our web page is presented instead of the original example.com. And just to further show that it works, let's open up actually a new machine. So I've opened up a new machine called the victim machine. This is just another client on the network that utilizes the DNS server to resolve names, and it's just a demonstration to show that not only the attacker machine sees this hacked website, but also anybody on the network that relies on the server to resolve addresses. So what I'm going to do is I'm going to go into Firefox and just going to clear the cache. I'm just going to clear the cache, and then what I'm going to do is also go on example.com here, and you'll see it resolved to 192.168.1.1, which is our Firefox address, or our attacker's address. If we go further down here, we can actually, let's exit out of here and then re-dump the cache. We can actually see www.example.com and see all of these addresses that we try to resolve, all these domain addresses will be resolved to 192.168.1.1, indicating that our attack is indeed successful. So not only does www.example.com work, but if we go back to the victim and try something like 12345.example.com, we'll get the same result. And that is a demonstration of remote DNS cache poisoning, where we did not sniff any of the traffic network because we are simulating a remote attack where we don't necessarily have access to maybe looking at all the packets in the network. Instead, what we did was more or less brute force the transaction ID in an attempt to forge a correct response, and then poison the server's cache itself, rather than continuing having to respond manually to the client. So now anybody in the network that tries to resolve an address within the example.com domain will be resolved the wrong address, 192.168.1.1, which is the attacker's address, and they will end up seeing this hacked web page.